Hey everyone, welcome to your Friday pre-recorded lesson. Today we're going to work on two more examples. I just have one more example involving the trapezoid rule and another example involving Simpson rule. So without further ado, let's jump into those questions. So we are going to be estimating the following integral using the trapezoid rule and 6 subintervals. So our function here is cosine of x cubed plus x. And we're going to, again, just kind of try to break this down step by step. I always start by trying to calculate delta x. And delta x is given as the difference of the endpoints divided by the number of subintervals we're using. So in our case, we have 1 minus 0 over 6. And, ooh, that's not going to be a fun decimal number, is it? 1 over 6 is, yeah, about 0.17 or so. So this could be a little bit painful. So let's stick with fractions in this case, mostly because this decimal number doesn't like it's a repeating decimal number. So I want to be careful not to round too much as I'm going through the process here. For using the trapezoid rule, especially since I know the trapezoid rule is a little bit fussier when it comes to the approximation. So there's our delta x. Our next step is to break our subinterval from 0 to 1 into 6 pieces. So let's go ahead and do that. We're going to bust it in half. So this is going to be 3, 6, or 0.5, and then each of these should be broken down into 3 equal-sized pieces. So here are our subintervals. So for example, the first subinterval should go from 0 to 1/6, and then we'll go from 1/6 to 2/6, and we keep doing that until we get up to 6/6, which is the number 1. And the trapezoid rule does have to use all of the endpoints along this subinterval, so we're going to highlight all of those in green, and I usually recommend putting down the weight factor as well. So our outermost endpoints, we only need 1 copy of those, but all of our innermost endpoints of those subintervals, we're going to need a weight of 2. So this is pretty much the setup for the trapezoid rule. So we're going to write down, we know our xi numbers are 0, 1, 6, 2, 6, 3, 6, etc. So now we just need to calculate the heights of all of the endpoints of these kind of upper regions for our trapezoids. So let's go ahead, let's using f of x equal to cosine of x cubed plus x, let's just start calculating some of these values. And maybe I'll just write down some, I need to shrink this screen just a bit so I can pull the calculator into here. So let's calculate cosine. Well, cosine of 0 is 1. I'm pretty sure that is the case. I calculated cosine of 1. That is not correct. Sorry, my mouse is like freaking out and it's bothering me. Okay, I think we're good. Okay, so cosine of 0 is 1. The next thing we need to do is calculate our function evaluated at 1/6. So we need cosine of 1/6 cubed plus 1/6. It's going to be a little bit of a pain in the butt to do because we're working with fractions, but we should be able to get a rough decimal approximation. So let's go ahead and I'm just going to, let's throw the cosine back in. And how do I want to do this? Let's put a set of brackets with our fraction inside. And we'll raise that to the power of 3. So there's 1/6 cubed, and then we want to add another 1/6 to that on the inside. And close up that bracket. And if you're using the calculator, I recommended make sure you have your radian symbol up top. We want to do this calculation in radians since we're using a trigonometric function. And we'll slap that equal sign and we get about let's take 0.9854. So 0.9854. And then we're basically going to keep repeating this process for all of our different fractions here. So I'm going to do the rest on my actual calculator here because it seems that the calculator for some reason has died and I don't want to type all of the stuff back into that calculator again. I will show you how to utilize Maple as well. So Maple can be quite help, I think, especially with these kinds of approximation questions. So for 2/6, I just kind of repeated the procedure up here, putting a 2 in the numerators, and I got about 0.9322. And yeah, the calculator is quite nice because you can kind of use the back buttons and go back, remove some of those numerators, and switch them up and get that updated decimal without too much button pressing here. So for 3/6 or 0.5, I got about 811. And there's a few more to do here, so F at 4/6 is about 0.5711. For 5/6, I got 1581. And then the last one's not too bad. It's F at 1, which is going to be basically cosine of 2. Which I get a negative number. I get negative 0.4161. Okay, so with those heights of those approximating trapezoids, well, these are going to be the endpoints of those kind of line segments up at the top, we should be able to now put this all together utilizing that formula. So I'm going to pull out the formula that we saw from class, which looks like the following. We're going to say trapezoid with 6 subintervals, or I guess we haven't really been writing that. We've been actually using the integral. So from 0 to 1 of cosine of x cubed plus x. We can approximate this using the trapezoid rule, which is delta x divided by 2. And then inside here we're going to have f at 0 plus 2 times f at 1/6. And we're going to keep doing the multiplication by 2 until we get to 5/6. And then finally, we'll add to that f at 1. So we get 1/6 divided by 2, and then let's start calculating some of the numbers that are going to go inside the brackets here. So f at 0 is just the number 1, so nothing too exciting there. Let's calculate 2 times this first thing. 9854. So we get like 1.9708. So 2 times the next thing. And that's like 1622 for the third one. So that's 3/6. Moving into 4/6, so 5711 times 2. And 2 to finish up here, so I need to multiply the 5/6 by 2. That's going to get us here. And then finally, we don't need to multiply this last one by 2. We're just going to be subtracting 0.4161 at the end here. Alrighty, so we could convert this first thing to a decimal if we wanted to. Let's go 1/6 divided by 2. That should be 1/12. And as a decimal number, we're going to get something that's roughly looking like this. So 0.8. And let's take 2 more decimal places. So it's 0.0833. Okay, so wish me luck. And I get a final decimal approximation that looks something like this. We get 6247. So that's 4 decimal places of accuracy here throughout that computation. So hopefully that's going to get us pretty close to what the true answer is for utilizing the trapezoid rule. Let's bounce over into Maple, so you can see how I might set this up in Maple and execute this, and we can kind of double check this decimal number as well. So of course you can utilize, I believe the integral calculator will give you, it'll probably give you the direct answer, so it probably won't give you an approximation utilizing the trapezoid rule. So you might be kind of stuck with the integral calculator being unable to do this for you. But if you're decently good at computing some things in Maple, it's not too challenging to kind of get this set up and ready to go. So of course, just having our restart command here, inputting that function f that we're working with, I'm deciding not to do, let's see, what do I want to do here? I actually do want to do the f of x command here. Okay, so I have my function set up. I have my dx set up as 1/6. And then I have the trapezoid rule with 6 intervals set up. I've just called it T6 to represent that I'm using a capital T for the trapezoid rule, and this _6 here representing the idea that we have 6 subintervals that we're working with. I do need to multiply by dx over 2. So at the front, I need delta x over 2. And then I can start filling in those numbers that I know go inside of my function. So I need to evaluate f at 1. I need to evaluate 2 times f at a 6th, and so on. So if I fill in all of these numbers here, hopefully Maple will be able to double check that final answer for us without too much worry. This should actually be a 0 over here, right? Boom, boom. Okay, so cross our fingers. Okay, so Maple's going to spit out some stuff. Let's tell Maple to convert that into a decimal number. So we're going to ask it to evaluate percent. Okay, so I basically just came back up here. If I hit the enter key again, that'll reevaluate that, so it's the last thing that's inside of its memory. And then the evalf command should give us a pretty good decimal approximation. Maple's set to do this, to like 10 decimal places or something like that. So that looks good. We got, I think, we got something pretty close, right? 6247. So we're a little bit off because of rounding. So Maple will give us a little bit more of an accurate answer. But, you know, for the sake of doing it by hand with a calculator, we did not too bad. Not too bad. Okay, so there is another, the final example of the trapezoid rule. Basically set up like all the other rules. We just need to keep track of all of the numbers along the subintervals, find all of the heights of the endpoints of our trapezoids, of our vertices of the trapezoids. Remember that it's delta x over 2 because it's an average of the left and right hand side endpoint rules. And that's where the weight of 2's come from for all of these things that are in the middle as well, just so you know. Okay, putting it all together, Maple verified that we were pretty close to what we needed to get to, which is a good thing. So that should finish up the trapezoid rule for us. Let's redo that example, and let's see just how much more accurate we can get using Simpson's rule. So same integral, we're going to go from 0 to 1, 6 subintervals again, so we know that delta x is going to be equal to 1/6. And we should actually have a bunch of the numbers that we need from before, too. But let's draw out that interval from 0 to 1, just so you can kind of see how I might think about and process this one a touch differently. So still taking our interval from 0 to 1, breaking that up into 6 subsections, and labeling those 1/6, 2/6, etc. So if I hadn't done that trapezoid rule example, I would still do this, and I wouldn't use decimal numbers like we have in some of the previous examples, because I know that 1/6 isn't a very nice decimal representation. It has a repeating decimal. So if you are running into a case where you have a repeating decimal, like, don't convert that till pretty close to the end of your calculation. We didn't actually convert ours until we got to that second last line, right? So if we go back to our trapezoid rule, we didn't actually convert our fraction into a decimal till pretty close to the end, just to allow us a little bit more flexibility in our calculation, a little bit more accuracy. Now, when it comes to the Simpson rule, we have, again, a weight of 1 on the endpoints of the outermost points of our interval, 0 and 1, and then we alternate between 4s and 2s. And essentially, this alternating pattern of 4s and 2s allows, Wikipedia has a really great visual of this, so if you want to see this, I would recommend going to Wikipedia, where essentially it takes 3 of the heights and tries to calculate an approximating parabola to top at the top of that rectangle. So instead of having like a flat surface at the end of that approximating rectangle, it kind of curves it and uses an approximating parabola. And so we get this alternating sequence of 4s and 2s at the expense of using this different kind of approximation method. But the execution is very similar to what we would do for the trapezoid rule. I still would probably start by trying to calculate the heights of all of these x values. So I have all these x values that I need to calculate heights for anyway. Just some of them are going to get multiplied by 4, some of them are going to get multiplied by 2. So actually what I'm going to do is probably just go back to the previous slide here, copy and paste some of those numbers. And then we can kind of get to this one a little bit faster. So these numbers aren't going to change on us, right? These numbers should be consistent for both examples. So I'll give you a few moments here just to copy those down if you need to. If you need to, you can always pause the video too to copy those down. So no need to calculate those again. We've already done that. So what we want to do next is we want to put this all together utilizing the Simpson's rule formula. So we are approximating the following integral. By taking delta x, and I believe we're dividing by 3 if I remember correctly. Trapezoid, Simpson rule. Yeah, Simpson rule is a division by 3. And we utilize the following formula. So f at 0 is going to go in by itself. It has a weight of 1. And then when I move over to f at 1/6, I'm going to have a weight of 4. So I begin with the number 4, and now I alternate back and forth between 2s and 4s. My second last one should end on a 4, so I'm kind of being mindful of that. The second one always has to be a 4, and then eventually over here I'm going to get a 4, and then plus the last one, which is f at 1. So I'm just kind of looking at that pattern and making sure that happens in this particular question. So next one's going to be a weight of 2, f at 2/6. Then a weight of 4. I'm probably going to need a bit more space here, so erase that. So a weight of 4, f at 3/6, and then a weight of 2, f at 4/6. And then we see it here, a weight of 4, f at 5/6. And my last one is f at 1. So I know that I've done the setup and execution correctly if the second and the second last both have a weight of 4. And this is with regards to the Simpson rule. Okay, so let's do a calculation. Delta x is 1/6. So let's take 1/6 and let's divide that by 3. That's going to be 1/18. And 1/18 to 4 decimal places is 0.0556. So it's 0.05 and the 5 keeps repeating. So this is rounded to 4 decimal places just to try to get a little bit more accuracy for us. And now I'm going to start calculating these weighted numbers. So obviously f at 0 is still 1. We have to multiply this first number by 4. Okay, second number here. or well, I guess third number multiplied by 2. All right, so next number, 0.811 times 4. Oh, next number by 2, so 5711, we'll multiply that by 2. We have our 0.1581 by 4. And then we're going to have that subtraction of 0.4161 at the end here. So that should be those heights just weighted by either that factor of 4 or factor of 2. And we can double check. So 1, 2, 3, 4, 5, 6, 7. Yeah, so it looks like I have all of them. Let's put this all together and get a rough decimal approximation and see if that matches up with what Maple says should be the case. Okay, and I get a decimal approximation that's like 0.6343. So there's 4 decimal places of accuracy. And what I'm going to do is I'm going to go back into Maple and just use Maple to double check this decimal number, because Maple will be able to give us a little bit more of an accurate final answer, because Maple won't be rounding so rigidly like we are. So let's go and take a little peek. So again, I have just the shell set up here for the Simpson rule. I'm going to call it capital S, and I use an _6 to just remind me that there are 6 subintervals here. We need to take our delta x and divide by 3 in this case. And we know what all of the x numbers are. We have 0, 1/6, 2/6, etc. And notice that I've weighted all of these by the appropriate number as well. So 4 times the first one, 2 times the second one, and so on. Okay, once again, Maple's going to spit out this really lovely number that's of no use to us because that is not a decimal number. So we're going to eval f% that, and Maple's going to tell us that using Simpson rule, we should get about 0.63378, which I think is pretty close to what we got, 6.3. So we're a little bit off because of rounding here. So we're not quite as accurate as we could be, but we're close enough that I'm not too concerned. But notice that Simpson rule really does require, if I wanted a little bit better accuracy, I probably could have calculated all of these up here to a couple more decimal places. So it never hurts when we're doing this by hand to add on a couple more decimal places. It's just gonna, especially with Simpson's rule, that's very, it zeroes in very quickly on what the actual net area is. So the more decimal places of accuracy typically that we give the Simpson rule, the closer we're actually going to be to what the true area is. The true net area is bounded by this curve. So if we were to actually ask Maple to integrate this, so this function, let's just go f in between 0 and 1, and let's see if it'll give us, no, you don't like that. Perfect, and then we can evaluate that. So there you go, this is the true net area using Maple, so 0.6334446. And you can see just how close Simpson's rule is, right? It already has captured about 3 decimal places of accuracy just using 6 subintervals, where the trapezoid rule has only got 1 decimal place of accuracy using 6 subintervals. So yeah, Simpson rule, the more decimal places we can use if we're doing calculations by hand, the better. I typically recommend 4. And that way you're going to at least get a couple decimal places of accuracy. But of course, if you use Maple, you're going to get the most accurate final answer here. So yeah, I like to use Maple just to kind of double check and make sure I'm in the right ballpark. As you can see, it gave us a pretty good indication that the Simpson rule was right. We had 2 decimal places of accuracy there. And our trapezoid rule, I think, had even more, right? Our trapezoid rule was pretty good, right? It had 3 decimal places of accuracy. So ours, of course, differed from Maple just because of that little bit of rounding that we did along the way. So don't be worried if you go to put something in Maple and you're out, the 3rd or 4th decimal place. That's not a big deal. What would be a big deal is if I went into Maple and it gave me something like, 0.75, blah, blah, blah. And I'm going back here and I'm like, the Simpson rule should probably give me something that's pretty close to what Maple gives me. So, if you're out by too much, you've probably done some kind of calculation error. And like I said, typically what happens is you make an error in one of the decimals. That's a very common thing. So go back, and that's why I kind of like to write out a couple steps so you can kind of see where my decimal numbers come from. And that way you can check your decimal numbers. And the other common mistake is not to put your calculator into radians. So just be mindful of that too. So keeping your calculator in degrees for those of you that are in physics is often a downfall in these kinds of questions. So yeah, other than that, hopefully you found the extra couple examples helpful. And the setup, I find the setup to be not too bad if you kind of intuitively think about it using a real number line. That usually is good enough to kind of get you the heights that you need, and then you just toss everything into a formula. So that's everything I want to show you for Friday. That means next week we will come back and we'll be chatting about series again. So we're going to move back into series and see some more tests for how to tell if a series is convergent or divergent. So that's the topic for most of the rest of the course, is a series and determining divergence. So I will see you guys on Monday. Have a great weekend.